Okay, lecture 21. Today we will do a bunch of examples involving the outputs of a multiple linear regression from Excel. And let's start with the first question. A meteorologist wants to determine if there's a relationship among the air temperature, wind speed, and wind chill temperature. And Excel returns the following analysis. Okay. So this question is really about whether you understand the output of an Excel analysis, because even if the Excel gives you these values, if you don't know where these come from, what they mean, then it's useless, right? Okay, so let's start trying to answer one by one. First, how many predictor variables are there? And I think one of the things that I was surprised is that even when I'm doing all this, some of you don't understand what business we're into. Like, what are we trying to do? Well, see, read the question. That's the first thing you should do. You're trying to predict what? Yes, so you're trying to come up with a multiple linear equation to predict the air temperature, right? By using what? Wind speed and wind chill temperature. Those two things, okay? If you're given those two values, can you actually predict the temperature? Okay. So those are the, oh, actually, it seems like if I read this, it looks like the air temperature and the wind speed are given, and then from that you have to find the real chill temperature. Okay, so that, I got to slightly backwards. So your prediction, you're trying to predict the wind chill temperature from the air temperature and wind speed. Okay, so how many predictor variables are there? Huh? Two. You're trying to use two to predict the third one. Okay, so those two, the air temperature and the wind speed, are called the predictor variables. Yes. Huh? What question do you have? Hmm? Do you have the previous? So what we are doing is the handout from last week. Who's missing the handout from last week? I only have 3 copies. Most of you must have gotten it.
I'll share with him.
Okay, okay. You don't have it. You should have it somewhere. Okay, so predictor variables are 2. Okay, how many lines of data are there? That's so we're trying to find the value of n, right? And there is no way, nowhere here that gives you the value of n explicitly, right? So instead, what you have to do is you have to use the degrees of freedom. Okay? And as you can see, the degrees of freedom of the regression is the number of the predictor variables. Does anyone know how to get the residual degrees of freedom? What's the formula for the residual degrees of freedom? N minus 2 is if you have a single or simple linear regression, okay, where there's only one predictor variable, okay? In that case, it's n minus 1 and n minus 1, which is n minus 2. What's the formula for the residual degrees of freedom if you have multiple linear regression? Anyone know? Just take a guess. I just explained it almost. Anthony, I think you know. What's the residual degrees of freedom? What's the formula for the residual degrees of freedom? Yes. No, no. Yes. No, no. Well, here it's n minus 3, but what's the formula in general? Huh? Uh, no. Anyone? No? Almost, almost. Okay, it's n minus 1 minus the number of predictor variables. Okay, so this 11 is equal to n minus 1 minus number of predictor variables. Okay, but how many predictor variables do you have? You have 2. That's the degrees of freedom of the regression, right? So now you know that 11 is equal to n minus 3. So you know that this must be n equals to 14. So that's how you get the number of data pairs. Okay. So the data pair that this person must have used in finding the multilinear regression equation must have been 14 pairs of data. Okay. Not it's not triples because you have the value of the air temperature, comma wind speed, and the wind chill temperature. So those are 14 triples of data is given, and that's what was used to produce this thing. Okay. All right. Now let's write the multiple regression equation. So for this, we must define some variables. So let me just delete the ABC, and then we'll define some variables. Let's say x1 is the air temperature, and x2 is the wind speed, and y hat well, let's just use y. So what's the y? The thing that you're trying to predict, right? Wind chill temperature. Okay. And now you have the formula, the predicted value of y. The predicted value of y equals, it's the general form is b0 plus b1 x1 plus b2 x2. And I stop here because there are only 2 predictor variables. If there were more, then you would have b3 x3 and so on and so on. But now what you need to do is you have to figure out what these b0, b1, b2 are from this Excel output. Okay. So can you yeah, I only go up to 2 because there is only x1 and x2. There are 2 predictor variables. Okay. Okay, who can tell me what b0 is by looking at this table? What are these things called? b0, b1, b2. What are b1 and b2 called? Coefficients, right? Okay. Do you see the word coefficient in the table? Okay. So judging from that, can you tell me what b0 must be? No, that's b1. Okay. Yes, yes, that's the correct one. Okay, so negative 12.5091. Okay. And then b1 is 1.3341. And b2 would be what? Can you tell me the b2? Negative 0.4143. It's all here, right? These 3 numbers. This is b0, that's b1, that's b2. Okay. So that's the answer. Okay. All right. Next question. What percent of variation in wind chill temperature is explained by the combination of variables in the regression equation? Okay, so we've used this a lot. What percent of variation is explained by the multiple linear regression? Okay. What value gives that? Do you know? Huh? No. Yes. That's the adjusted R squared. Do you know the name of that thing? R squared. It's called, no. Well, okay. So there's a formula for that that's dependent on the correlation coefficient R. But I was asking for the name. The name is the coefficient of determination. Okay. So the coefficient of determination is 0.9912. So therefore, 99.12% is the answer. Okay. Okay. Do you want me to explain anything again? Yes. So adjusted R square right here, 0.91912. That means 99.12% of the variation in the wind chill temperature is from the multiple regression. Okay, so the regression equation explains most of it. Okay. Is that value R or it's R squared, right? Yeah, the R squared value is close to the correlation coefficient lowercase r squared. Okay. However, the formula is if you actually want to know the formula, let me just delete these so I have room. So adjusted is given by the following. It's 1 minus, it's the degrees of freedom of the residual divided by degrees of freedom of total times 1 minus r squared, or lowercase r squared. Okay. So what it does is that it's a bit hard to see from here, but what this formula really does is it penalizes for having too many predictor variables, because if you have too many predictor variables, you can overfit the prediction just that way. Okay. All right. And this is called the coefficient of determination. Okay. Now let's try to answer these. Let me take that out, put it in here. Okay. We just had a quiz on this, so you probably have a good idea what to use. What do I use if I want to predict? Yeah, the regression equation. We just use the multiple regression equation, which we found right here, right? So we are going to paste it right here. And what we need to do is just plug in the numbers. Let me just make this smaller. Okay. Okay, so I have outside wind temperature is 12. So from this formula right here, I just have to plug in 12 and 32 into x1 and x2. So let's see, 12 and x2 would be 32. Okay, let's put that into the calculator. Negative 12.5091 plus 1.3341 times 12, then minus 0.4143 times 32. And you get negative 9.75. So the answer is negative 9.75 degrees Fahrenheit. Okay. And it kind of makes sense because, you know, if the outside temperature is 12 degrees Fahrenheit, but if the wind is 32, is that like a heavy wind or like a gentle breeze? It's a heavy wind, right? So do you expect the wind chill temperature to go down, way down, or almost the same? It should go way down, right? Because you have heavy winds. So that's why you get negative 9.75. Okay, determine the overall significance of the predictor variables on wind chill temperature. Okay, now here is where you really need to pay attention because everything that we did so far is kind of straightforward. If you just read the solutions after class, it will be really easy to follow. But what's not so easy is this F, okay? So everyone please pay attention to the screen, okay? All right, first thing first, MS, okay? So how do you get the mean sum of squares? That's defined as sum of squares divided by degrees of freedom, okay? So let's see what goes in right here. So what this question is really asking is, if you actually look at the Excel output, it has numbers in the MS column and also numbers, it has a number in the F column. And after that, it also gives you the probability p-value P. And you have to figure out what to put in the MS and you have to figure out what to put in the F. And only after that, you can figure out what the p-value is, okay? So let's first figure out the MS's, okay? So what is our MS? The two values are 3914.7949 divided by what? Can you tell me? 2, right? So you have to divide 3914.7949 by 2. And 1957.397. Okay. And then for the second MS, you don't have to find the total MS. That's meaningless because the F value is the ratio between these two. So we now have to do 29.2051 divided by what? 11, yes. So that's what you have to do. 29.2051 divided by 11. 2.655.
Why couldn't you just do like the overall total?
What was the question?
Why can't you just do the overall total PF? That sense. Like, why do you have to do them individually?
Oh, because we okay. So the question was, why do we have to calculate these individually? Well, that's because in the multiple regression, so there's something about having a lot of predictor variables being more advantageous in predicting the thing. So if you can predict something with like 100 different data, 100 predictor variables, that's not very significant. It's not impressive. Okay. So you kind of have to figure out not just how see the residual sum of squares. If this value is as small as you want, you can, if you can get this value sum of squares of the residual to be small, that means the difference between your predictor and your regression and the actual value, the predicted value and the actual value are very close to each other, right? That's what sum of squares being small means. Does that make sense? First, here I'm asking you to understand one thing first, okay?
Yeah.
This sum of square, I want this to be small.
Yeah.
Because if this is small, that means that there's less error in your prediction, okay? However, uh, this value right here, the the data itself, the predictor values, if that value is made of a lot of degrees of freedom, then uh, it it can actually reduce this sum of squares without really doing much. Okay, so I don't know how you say it. Okay, so here's another way to say it. Uh, if you want to have some prediction about the lifespan of one person, okay, I want to predict how long he's going to live. Okay, now you might have a regression equation with just blood pressure only. Okay, that'll be hard, right? The R square will be pretty small, right? Then you add in blood sugar and whether this person is obese or not, right? So BMI could be another one. And you start adding more and more things, right? And you add things like that. Has this person ever in a big accident? Did he have a big surgery? You put a lot of different predictors in there, and the more you put in, the better your adjusted R square is going to get, right? Does that make sense? Okay. So increasing the predictor variables will inevitably increase the R squared. Okay. But some of them might just be a fluke because your data size might not be like, it might be just 100 patients and you might be using thousands of predictor variables, which happens in that case, what happens is that if you know the predictor variables, you can basically identify which patient it is. Then at some point you're just able to figure out who that person is and then end up with a very good accurate prediction, which is not really predicting because you're just really identifying each person. If such a thing happens when you're predicting, it's called overfitting. Okay, and that's not doing a good job. So uh, what we have here is like we're trying to see the significance, the p-value. If the p-value is smaller, you say it's very significant, right? Uh, and to get that p-value uh, in the multiple regression, not only you have to be considering the residual value, but also the number of predictor variables. So these two things should be fed into some probability distribution. And that one is handled by something called the F distribution. F distribution is like it shows you what happens to ratios of two sum of squares uh, with some given number of degrees of freedom. Okay, so that's what you do. And from that, we have the probability P. So because of that, the total is not really doing much. It's really these two things that you have to know. Okay? All right, so it's a bit hard to explain everything without the hard math, but that's I try to be as specific I can. P-value, we're far from there. Okay, so I just told you what to put on the MS. Okay, so let me see. I'll just copy this. So I'm saying that this value goes right here as the MS, okay? And then right below it, right here, 2.655 goes right here. Okay? And now what do you do with the f? How do you calculate the f? F is the ratio of the two mean squares, okay? So it's 1957.397 over 2.655, okay? So that's what you have to calculate, and the f value is therefore 1957.397 divided by 2.655, and that gives you 737.249. 737.249. 737.249. Okay. And let me copy that over here as well. 737.249. Okay. Okay. Now what you do is, yes. What?
Will the chart ever have more values, or is this just going to be?
The question was, would the chart ever have more values? Yes. For some questions, I would give you the MS, and you have to find the FN afterwards. Okay. So would it have more than two MSs? That the answer is no. Okay. You will always have just two mean squares because F distribution is the distribution of ratio of two sum of squares. Okay. So it will always be this one. Okay. Okay. So now we have to find the p-value. How do we find the p-value? This is how it works. It So p-value, the F distribution also look like the chi-squared. So it has this half bell-shaped thing. Starts from 0 and goes like that. And we always do a right tail test. So the p-value would be the area under that distribution from this starting value 737 until infinity. Okay. So that's what we have to do. We have to do second vars. You have to do FCDF. And then what you put is 737.249 is your lower. And you have to go up till infinity, but there's no infinity in the calculator. So you just put a big number. What should I put in?
5.9.
No, that's too small.
1,000.
1 million, yeah. Yeah. Or 10,000 is fine as well. Okay. But it has to be something quite bigger than this number. Okay. All right. So now, what's the degrees of freedom of the numerator? 2, right? Yeah. What's the degrees of freedom of the denominator? 11, right? Yeah. See, we're taking these duration, and if you look at these, what were the degrees of freedom to produce? It was 2 and 11, so you put those in. Yes, you have a question? No. Okay. You paste it, and the result is 1.915 and 10 to the negative 12. So the p-value is p equals to 1.9, what was it? 116 times 10 to the negative 12th power. Okay, so that's your p-value. Okay, so that's the significance. So the overall significance is the p-value, and the p-value comes out as very significant.